Alrighty. Okay. All right, so your programming test number 2, we are busy grading it. We should be able to get a result and feedback back to you by next Monday. You can expect a result by early Monday, I think. Okay, you can look forward to my e-class announcement. And for your written test number 2, it will be the last test for the semester before the exam. And it's going to be next Wednesday. So for that one there, I'm going to release the guide to you about the general coverage, but you can assume that it's going to cover basically the bridge controller from the beginning until what we're going to cover on Thursday, including it, right? So you got sufficient time to study for that. And I will also release some questions for you to maybe make some reference about. Maybe tomorrow or maybe slightly later in the week. But your safest bet is to start studying for the bridge controller. And for the lab session tomorrow, there's no lab session tomorrow, just to let you know. But we're going to make sure we release the lab number 5 to you very soon. You can get busy with it. All right, any questions? Any questions you want me to clarify before I start the bridge controller again? Alrighty. Awesome. Let's do a recap as usual. So today we're going to dive even deeper into the bridge controller, and we're going to talk about some very tricky refinement condition called guard strengthening. That's something we'll do today, but one step at a time. All right, let's do a quick recap just to make everybody comfortable so we can start on the same page. So last week, we basically spoke about this particular failing deadlock freedom condition. So basically that one, they really have dived deep into the proof. And this one here is about the deadlock freedom proof for model 0. So when you study for that particular proof, you want to see that when we reach this particular stage, the model solution told you to really go for EQLR, but alternatively, which I showed to you last time, you can try EQRL. That one there is also going to lead you to some unprovable sequence over there. And that one there, if you try to fix the model accordingly, as I explained to you last time, it's not going to be reasonable. So that's why every time if you got into some unprovable sequence, you got to think to yourself, is that a worth fixing condition for your model? That's something you have to judge. All right? And then instead, we try to look at this particular unprovable sequence instead. And we found that the unfixed model actually allows a particular condition where the maximum number of cards will be equal to 0, which is going to cause deadlock for both events. Right? You can really look into how the deadlock is going to occur. And then we fix the model, and we discharge all the approved obligation that's to do with deadlock freedom. And that will be the initial model summary. All right, that's basically about M0. So when you study for M0, you really want to pay attention to, number one, how did we come up with this particular d larger than 0 constraint? Not just to memorize it, that's not the way to go. You want to see how we actually got into the initial unprovable sequence and get into this condition, number one. Number two, how did we actually got into the unprovable sequence for invariant preservation for M0, and how we came up with this one here and this one here. All right, so that's the highlights for you. And other than that, you can see nothing is new. We got constant, we got axiom, variables, invariant. That's going to be true for every model we're going to see. Okay. Any questions about the initial model M0? All right, so I think for the next written test, we can, as usual, we can hold some Zoom review session. Possibly Sunday or Monday, I'll confirm the time. So for those of you who can join, you can join. And then you can ask me questions about the bridge controller as you study more about it. Okay, good, that's about M0. I'll leave you to study that. And then we talk about this first refinements. And the essence of it is we go from basically where the island and the bridge has no distinction, meaning that we kind of consider them as a compound where we got only one variable n. But now we try to split this compound into two, into the island and also the bridge. So that's the main concreteness we have added to the first refinements. So you think about this part over here is the island, and this part here is the bridge, and that's the mainland. So that's why we got 1, 2, 3, and 4. 4 different events to really consider, especially ML out, ML in. These 2 events already exist in the initial model. So we call them we call this pair over here the abstract events or the O events. And ML out, ML in, they are more like an overridden version of the events, like a Java terminology, right? So these 2 are the concrete events, which we're going to speak more about. And ILM, IL out, we're not going to touch them just yet. These are so-called new events, which we're going to deal with separately. So every time you talk about refinements, you want to categorize the event into 2 groups. The first group will be the overridden version from the previous abstract model. The second group will be the new events that we newly introduced. All right? That's something to note. All right, and then we spoke about the abstract concrete will be more like a relative. So whatever, when you compare M0 and M1, this will be abstract, this will be concrete. Later on, we're going to have another second refinement, M2. So when you compare M1 and M2, M1 will now become abstract, and M2 here will be concrete. So it's really relative as opposed to absolute. Okay, and we talk about the abstract, the states of the first refinements. We got A, B, and C, right? You can think about A here is the traffic flow from the island, the traffic flow from the mainland into the island. On the other hand, we got C here, which will be the traffic flow from island into the mainland. Of course, A and C cannot be larger than 0 at the same time. Otherwise, it's not one way anymore. And we got B here, which will be the number of cards on the island. And the invariants over here are the type invariant, just specifying the types for A, B, and C. That's pretty straightforward. And for invariant number 4, this one here is what I call the linking and gluing invariance. It's linking the abstract states and the concrete states. So if you look at it, this is the invariant here. So this N here is the abstract states. That's the variable in the M0. A, B, and C here are the variables at the concrete state M1. And we try to link them together by this equality here. Okay? Versus invariant number 5 here is about more like a functionality, like safety invariance. We're saying that either the traffic to here should be nothing, or the traffic here would be nothing. You cannot have both flow at the same time, right? That's why either of them should be 0. It's okay for both of them to be 0. That's fine. At least you have no collision. All right, we got these 2 invariant conditions here. All right. And that's the final part that we spoke about last time. Let's do a quick recap. And we try to look at the 2 concrete events, ML out and also ML in. So ML out has to do with some cars that wants to go to the island. So they kind of go into the bridge over here. And we said that there should be 2 guards that we need to put in. The first guard is pretty simple. That one is to say, if you want to go this way here, you got to make sure there is no opposite traffic coming. So that's why C here should be 0. That one's straightforward. Okay, that's the first guard. And the second guard over there turns out to be here A plus, let me see. Let me show to you. The second guard here turns out to be A plus B less than D. All right, that's a clean version. But the way we derive this A plus B less than D is by thinking about several things. Number 1, we think about the abstract guard in ML out. If you can go back to the M0 and look up the guard for ML out. That one there tells you N less than D. Okay? And then we know that the linking invariance, which is over here, tells us that A plus B plus C equals N. That's the second equation. And the third equation is, we know from our first guard over here, the opposite traffic over here should be none, right? So C should be equal to 0. So when we combine this equation, and this equation together, 1, 2, and 3, what we got would be A plus B less than D. Right? That's how we derive this particular concrete guard. Okay? Quite a bit of work to derive it, but once you derive it, it's there. That might be the trickiest guard to get through for this particular refinements. Okay? But the lesson is, if you want to come up with the guard for some concrete events, you may have to look at the constraint from the abstract model as well. That's the main lesson. All right, guys, any questions so far from the recap? Let's now move on. The next one will be, let's figure out the guard for this particular event, which is much simpler. But I do have some little exercise for you guys to think about. Okay, that's also worth thinking. Let's figure that out first. Let's say I give you some English description about the guard for MLN. So that is something we want to figure out. So when I say question mark, I might mean there might be one guard condition or might be several guard conditions. We don't know. But at least I know informally, when I say MLN, I know that there is a car. MLN simply is this event over here. We have some car that wants to go from the bridge back to the mainland. That's an MLN. All right? And informally speaking, the guard should be is enabled when there is some car on the bridge heading to the mainland. That's the informal description. Now we want to formulate it. What I'm saying is, if you actually want to have this MLN, there's got to be at least one car on the bridge. Otherwise, how can a car enter the mainland? Good? Any suggestion about expressing this? This is extremely simple. We do have A, B, and C. So if you want to express the guard over here, you definitely have to somehow use A, B, and C. But which one should we use to say there is at least one car on the bridge wanting to go back to the mainland? Anyone? Yeah. So if you talk about A here, but A is somehow the flow traffic over here, right? You can say that's 0. That's okay for now. But why does it have to do with B? Because let's say this. If B is equal to 3, it doesn't directly impact about this event over here. Because the 3 cars here may want to stay in the island. They may not actually want to go back to the mainland. So what we are really talking about is the number of cars on the bridge itself. So what you really meant to say would be maybe C here. Okay? We want to say that somehow the traffic flow over here should be at least larger than 0. We got at least one car on the bridge that wants to go back to the mainland. If you have no car on the bridge, how can the car go back, right? So it turns out this condition here would just be C larger than 0. All right, that's the guard. Okay, just make sure everybody is kind of catching up, right? It's been over the weekend, so you may have lots of recall of the detail, right? You may want to recall the details. So here's my question for you. I'll put it down. Which you kind of brought it up, which is good, okay? I'll put a question here for you guys. Is it necessary to add a new guard? Because we are saying that we actually want to go MLN. So there should be at least one car that's going back to the island. But should we say at the same time A should be equal to 0? Because we want to make sure there's no collision. Sounds sensible, right? So now should we add an extra guard to say A should be equal to 0 as well? All right, I'll put it down first and then I'll make it a little bit more elaborate. A equals 0. So here I'm talking about necessary. A new guard. So if you believe that's necessary, we should really add another one here to say A equals 0. But I'll put a question mark over here. Is it logically necessary or it is not necessary?
I don't think it's going to be necessary because I think that guard A equals 0 is going to be used for IL out.
Going to be used for ML out?
No, IL out.
Oh, that's another event, right? Yeah. Interesting. Ah, okay, I see what you mean. That's a very clever thinking, okay? So what your classmate is thinking is like this, which is kind of true, which you'll get to a little bit later. What your classmate say, I'm going to repeat, which you're going to see that later. Very, very clever. So when you say that this ILL over here, when we try to go out, you want to make sure the traffic here is actually no. So you don't have any collision. Okay? But there's another way to express this other than this. All right? You guys want to think about this, but for now, I'm just going to tell you how you can kind of formulate this question here. Okay, I'm going to box this over here. Okay, is it necessary? It turns out it is not necessary. It is not really wrong if you got A equals 0 as an extra guard. Nothing wrong, but it's just logically unnecessary. Okay. The way to show that it is not necessary is you can see that we already have some invariance over here to say either A is equal to 0 or C is equal to 0. That one should be sufficient to really show that based on this, we know that A should be equal to 0. All right, so now how do I formulate this? I'm now going to put a sequence over here that's for you to exercise improving. Okay, I'm going to put it here. So I'm going to say here, C larger than 0 is the guard that we just came up with. I got the existing invariance, which is over here, invariant number 5, A equals 0 or C equals 0. Does it entail turnstile that A is equal to 0? That's the question. If you're able to prove this one here, if you can show that this sequence here is provable, that means given C larger than 0, the guard that we just came up with, and given the existing invariance, it's logically implied A is equal to 0. There's no need to put it explicitly if you can show that it's provable. All right? Guys, this will be exercise for you. You should be able to prove it. All right? I'll leave that to you. Exercise. But the conclusion is you don't really need to put A equals 0 at this point. But you should really try to follow through the flow over here. Whenever you're trying to come up with a guard for some particular events, you want to give the minimum possible. You don't want to give any logically redundant guard. All right? It turns out this one here will be logically implied, so there's no need to put it down explicitly. All right, question? All right. Let me just make sure I don't have that. That might be distracting to you. One moment. Let me just put it back. Okay. Anyway, okay, there we go. It's gone. All right, if no question here, let's continue. All right, so let's have a very quick summary about what we have achieved so far, right? So far we have got this particular M1 over here. And then you can see that we got two invariant conditions over here. We got this one here, and we got this one here, right? So this one here is the linking invariance. And this one over here is a safety invariance. Both are valuable. The linking invariance basically is trying to link all the way to the abstract states, which is over here. Right? You can see we're linking it. Okay, that's something you can see here. And then we also talk about events. Think about ML out, ML in. So these are the concrete events. Over here. These are the concrete events. Here. Concrete events. And these two, the counterparts in the abstract model, these are the abstract events. And of course, the guards over here are the abstract guards. So these are the concrete guards, right? So basically just add abstract versus concrete to the guards, events, or action. Similarly, this will be the abstract action, and this will be the concrete action, right? Let me just say one of them one more time, because we're going to need that to formulate some proof obligation today. So think about this guy here is a concrete guard as opposed to abstract guard. So concrete guard. All right. All right, any question here? That's what we have achieved so far. All right. If no, let's now move on to the slides. All right, so we're done with this. And the next step is to understand about, okay, before, after predicates. Okay, let's see this. Okay, that one we can do that also quickly. Let's see, before, after predicate. Okay, I think before that, I would like to show you some transition first. Okay, so let's go back to iPad. Let's now try to put these two models together. What you really want to be convinced is whenever you're doing some concrete transition, for example, you want to do ML out. Whenever you want to go from some concrete states, pre-state into post-states using ML out, there will be some corresponding abstract pre-states into some abstract post-states where it's also linked by ML out. But this ML out is abstract. Sorry, this ML out is concrete. This ML out here is abstract. That's something I want to show to you, right? That's kind of the corresponding movement you want to be convinced. All right, let's now take a look at it together. And I want you to consider this particular trace. So I want you to consider this particular trace. Let's say init, followed by init events, followed by ML out, followed by ML in. All right, so we're going to see that after the inits, how are we going to see the correspondence between the abstract and the concrete models when they try to make the same transition ML out? Okay, let's see that. All right, so let's make the following assumption. We got the maximum number of cars is going to be 2, right, for both abstract and concrete, so we're consistent. And the initialization will just initialize n to be 0, and also ABC also to be 0. Okay, let's now take a look. So what I'll do is I'm just going to copy this. So this will be the abstract model. Okay, I'm going to put it here, abstract. And this one over here is going to be the concrete model. All right, so after the init for the abstract, we got n being equal to 0. That's easy. Okay. And after the inits from the concrete, we're going to set A, B, and C to 0, 0, 0. Okay, so this will be the very first pre-states before we take the ML out. You can think about after initialization, now we are in the pre-states before we take ML out. Okay, how do we interpret that? Okay, first of all, how do we link these two states together? This is the abstract initial states. This is the concrete initial states. This is the abstract initial states. And this one is the concrete initial states. And how do we link them together? The way to link them together, you got to look at the linking invariance over here, which is A plus B plus C equals N. And if you try to do that over here, let's say, if you try to link them together over here, right? So you want to quote invariant 1, 4. Now you got A plus B plus C, 0 plus 0 plus 0 equals N, which is 0. Check. That means we have some consistent abstract and concrete states after the initialization. Think about we are trying to create these two systems concurrently and trying to run them. Okay. Okay, I'm going to do basically one together with you. You can do the other one. Okay, let's do the first one, ML out. In order to really take ML out, we have to check the abstract guard. So now n currently is 0. 0 less than d, which is 2, that's true. So that means the ML out, the abstract version should be enabled, right? And that way, we're going to take ML out. ML out. So this is the abstract version. All right. What about the concrete version? Is it enabled? Right? The way to check it would be, so here you can see ML out over here. A plus B, which would be 0 plus 0 less than D, which is 2, true. C equals 0, also true. It's also enabled, right? So we can also take ML out over here. ML out. So this is a concrete version. And after this, we're going to have the resulting post states for each one of them. Okay, let's do one by one. Okay, so for this one here, so this will be the post states for ML out. That one's easy because n will just be incremented, right? From 0 to 1. From 0 to 1. And we're going to do the concrete version as well over here. And we're going to have the post states there. And I'm going to put it here. Okay, right here. A little bit smaller. There we go. Okay, that one there. What should be the effects for ML out in the concrete version? A should be incremented. So that means only this one here should be changed. So what we have is 0 to 1, 0, 0. If you only look at this one here in isolation and this one in isolation, you don't really see exactly if they are consistent. The way to check it is by quoting the linking variant to see whether it's going to be satisfied at the post state as well. That's something we're going to check. Okay? And then I'm going to, again, trying to link them together. And I'm going to use the same invariance. Invariance 1, 4. All right? So now, A plus B plus C will be 1 plus 0 plus 0 equals n, which is 1. Check. The same. All right? So you kind of see the idea. The idea would be whenever you're trying to have some concrete transition over here, there should be some corresponding abstract transition as well. That's my point. I'm going to write it down. And then your exercise will be try to go from here to see if you're able to do MLN. All right? So the remark will be for each concrete transition, there is always a corresponding abstract transition. That's what we learned from this particular example. All right, this one here. This one, corresponding abstract transition. All right, you can see here we got concrete and we got abstract corresponding. And this diagram here is so-called a commuting diagram, which I'm going to talk about a little bit more. Okay, for now, let's just focus on the example, but it makes sense, right? Okay. And this part over here, to really continue from here, this will be exercise for you. Exercise for you, try to do the transition to see if that's possible, and once you got the resulting states, you can also check the invariance. Okay. All right, guys, any question about this? Yes? You should check other invariant as well, but for now, I'm just saying in order to check if the both worlds are consistent, let's focus on that particular invariance. Yeah. And of course, guys, your classmate raised a very good question here. So when you actually go from here to here, of course, for this state in isolation, you should also check all the invariants on the abstract states. And for this post state here, you should also check that all the concrete invariants are also preserved, right? And for between them, the only thing that will be applied will be the linking invariance. That's the only invariant that's gonna involve both the abstract and concrete variables. That's why we're only checking it, okay? Okay, I'm gonna delete this, and then, so when you see the notes, hopefully that'll be less confusing. All right, if no further questions, I'm gonna do one more. Okay. Two more, actually, two more. And then we can take a short break. Question? I might know what you, yeah. So, but something we'll leave that for later. Yeah. So, but I think the general idea will be later on we might introduce other events. In which case, you also have to see how the new events gonna be has the correspondence in the abstract world. That's something we'll get into. Okay. But at least we'll focus on this one here for now. Okay. All right, so now the next one will be to talk about before-after predicate very quickly. Okay. Okay, so let's see here, before-after predicate. All right. You can also see it on the slide, but I will show you right away here. So we got the concrete events here and here, right? Just to remind you. So here we got the concrete events. The way to figure out the corresponding before-after predicate will just be the same, okay? And the only thing that's noticeable will be this. Just remember we got three variables. Recall the concrete variables are not just n. Well, in the abstract world, we only got one variable. That's pretty straightforward. But now we got a, b, and c. Right? So the way for you to figure out the before-after predicate is a little bit trickier. Not too bad. Okay? For example, if you look at this one here, this one specifically, of course, is going to be c prime equals c minus 1. So we are saying that if you try to make a transition using MLN, the post-state values of c should be equal to the pre-state value minus 1. Straightforward. However, if you only write this as the before-after predicate, it's not complete because you only have addressed c prime. What about a prime and b prime? So if you got multiple variables, make sure the before-after predicate address every variable. What should we say about a and b? They don't change because we say that we're going to let c become c minus 1. Implicitly, we are really saying a becomes a and b becomes b. But we don't really say that usually in Rodin. But you got to know the corresponding before-after predicate really means this. Okay? So what you really want to say is and a prime equals a and also b prime equals b. Right? So that's the part I want to mention. And you do need this because once we get to the invariant preservation proof obligation, you will need a before-after predicate to figure out the goal. All right, similarly, if you think about this particular before-after predicate, right, for this one here, well, that one we can do that very quickly. Well, solution here, but let's work out together anyway. A prime equals a plus 1, for sure, but you also need to address what's not mentioned over here, which will be b and c. They are not changed. And b prime equals b, and also c prime equals c. You got to make sure all the variables are mentioned. Okay, that's the only point I wanted to say. Okay. And let's do one more page, and then we'll take a short break. And this one here is going to prepare us for formulating some proof obligation, which will be new today. But before that, let's get some notation done. Okay. And again, it's going to be a dry one, but I'll make it quick and clear. All right, if you look at the slides, this part over here is something we just said. You got to make sure you cover all the variables. And then over here, okay, it's just about abstract versus concrete. And then, okay, so starting from here, slide 50. Okay, the two slides before are just about abstract versus concrete, which we also covered earlier. Okay. Now we need a little bit of some new notation to really cover the concrete world as well. The notation that we covered about 2 or 3 lectures ago, that one basically covered just the abstract states. But now we're going to talk about the concrete state as well. And we're going to go over the notation one by one. Okay. So it will be slide 50 and also slide 51 and 52. So these 3 slides. Right, let's now go over them one by one. Okay. First of all, let's talk about the variables. So here I got initial model, abstract. I got the first refinements, the concrete model. Before we know that what's V and what's V prime, right? Let's recall the details quickly. So before we know that V is, by definition, simply just N. And V prime will be the post-state value, which by definition is N prime. And now, since we got the refinement model, we got something called W and W prime. So whenever you see W or W prime in the formula in the proof obligation, you will know that it's referring to concrete states. Okay, what about in this case? We got A, B, and C. So we got W, by definition, would be pre-state value. A, B, and C. And W prime, by definition, would be A prime, B prime, and C prime. Straightforward. And we got another 3 groups. We got invariants, we got guards, and we got effects. Okay, let's go for one by one. This group over here talks about invariants. So we distinguish between I, which is called abstract invariance. Invariance from this world over here. All right? And when I has no index, we are talking about all the invariants over here. Okay? And what you want to notice is the C here is the constants. And the V over here is the abstract variables. Versus the C here is also the constant. That's the same. You know, potentially I should be able to use the same color. Let me just use that quickly. So here is also the constant. All right. And then, so here we got, this is the abstract variables. And this one here is the concrete variables. So what does that mean? That means when you talk about the abstract invariants, which are the 2 invariant conditions over here, for example, they can only refer to either the constants or the abstract variables. That's it. On the other hand, when you talk about J, which stands for the concrete invariants, which are the invariant conditions over here, in general, they can refer to constants, they can refer to abstract variable N. For example, you can see the occurrence of N over here in the linking variance. And also they can refer to the concrete variables, in which case you got A, B, C, AC, and etc. Right? That's what it means. So I will just write down what J is. Okay, so by definition, you can think about J here. So what's the constant? Constant is just D. And abstract variable will be just N. Concrete variable will be A, B, and C. And by definition, we got these 5 invariants. Okay. This will be the list of invariants. I'll say invariants 1, 1, dot, 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 all the way to invariants 1 and 5. 5 invariants. And by the way, if you remember the naming convention, here, the one here, the one over here is referring to M1. And the 0 over here is referring to M0. Okay, just don't forget. That's something we also spoke about. All right, so we are done with the concrete invariant. Just remember, for concrete invariants, you may also refer to abstract variable as well. That's the additional part. All right, these two are going to be very much needed after the break. Okay. Now we talk about the guards. So G over here is basically the guards in the abstract states, either this or this. And you can refer to some constant, in which case you can see the constant here. You can also refer to the abstract variable, which is n over here. All right. So for example, if you look at the ML out over here, for this event specifically, the G, and which can refer to the constant d or the abstract variable n, by definition, n less than d. That's the abstract guard. And we use the letter H for concrete guards. And for concrete guards, you can only refer to either the constants or the concrete variable. And notice one thing here. It's only the concrete invariant where you can also refer to the abstract variable. But for the concrete guard, you cannot refer to abstract variable. All right? And let's see one example for concrete guard. So now if I go to over here, let's say for ML out correspondingly. So what about the H? So we got constant d you can refer to. Also we got the abstract, the concrete variables. You can see W here, A, B, and C. By definition, for this case, it will be this one here. A plus B less than D, and C equals 0. That's the concrete guard. And you can do the same for abstract guard for this event here, or the concrete guard for this event here. I'll leave that to you. Okay. Final one. What about the effects? Okay. The effect is going to be similar as before. You just remember, for the abstract effects, you can only refer to abstract variable. For the concrete effects, which we use F to denote, you can only refer to concrete variables. All right, let's see some example here. Okay, I'm going to compare them side by side. So for this one here, you can think about the effects over here. We got D here, we got N. The effects of, let's say, ML out. You can see we just try to assign N to be N plus 1. Right? The effects is the post-state value will be just N plus 1. All right. On the other hand, the concrete effects for, let's say, ML out. That one there is going to be A plus 1 for A. But don't forget, we should cover all the variables. Okay? So we got F here, the concrete events. So we got constant D, and also we got A, B, and C that we can refer to, right? A, B, and C here, corresponding to the W here of the ML out. All right, that one there, we're going to follow the order. Remember the before after predicate. For ML out here, A prime is going to be A plus 1, so that'll be the first one. B prime is going to be B, second one. C prime is going to be C. So A plus 1, B, and C will be the effects for these three variables. Okay, let me write it down, and then we're done for this page. So we got A plus 1, and then we got B, we got C here. So think about this will be the post-state value for A. This will be the post-state value for B, which doesn't change. And this will be a post-state value for C, which also doesn't change. Dry, but we are done. Okay. And that'll be the notation for us to really survive through defining the guard strengthening proof obligation. But before that, I would suggest we take a break by taking attendance. Okay, so everybody be fresh when we come back. All right, let me pause the video and let's take attendance. All right, so now we are ready to talk about the new proof obligation. Okay, that one there is called, let me see the slides over here, guard strengthening. But in order to understand this one over here, we need to do some background check. Well, when I say check, it really means I want to give you some background for the guard strengthening. Right? Number one, we now want to understand what do I really mean when I say I want to strengthen the guard. The guard itself is a predicate, like a Boolean condition. What does it really mean for a Boolean condition to be stronger than another Boolean condition? That's number one, we want to understand. Number two, you will see that the actual proof obligation is kind of confusing. I'll show you first, and then I'll also need to explain. If you look at the actual proof obligation here, if you remember that, this guy over here, H, before the break, we said that H is the concrete event guard, right? The proof obligation tells you that in order to discharge this particular guard strengthening proof obligation, we need to make sure that the concrete guard somehow entails the abstract guard. You can easily forget, maybe it should be the abstract guard that entails the concrete guard, right? But this one is wrong, and this one is correct. That's a common confusion, so I also need to explain that. So two things we want to do before we get to this page. Number one, what does it really mean when a predicate is stronger than the other? Number two, why do we have to put that the concrete guard should imply the abstract guard? These are the second thing. All right, talk about one by one. Number one, let's now give you some background about what does it really mean when a predicate is stronger than the other one. You may have heard about this term, maybe in 1090. If no, let's now learn it. Okay. So we talk about predicates in general. And we talk about weaker versus stronger. And there's a simple definition to learn. All right, so this will be the number one thing we want to clarify. Okay? And you want to think about this particular logical relation, P implies Q. If I know that P implies Q is actually true, there are two ways to interpret this in terms of weaker versus stronger. We can say that P, the antecedent, is stronger than Q. You can also say equivalently, Q, the consequence, is weaker than P. All right? These two terms are equivalent. You can use either way. But I typically prefer to say which one is stronger. Okay? Doesn't matter. But let's see some example, and then I'll give you some idea about visualizing it, which might also help. Let's say, for example, if I got P here of X, by definition, it is X larger than 0. These are predicates. And also I got another predicate Q over here, X larger than or equal to 0. Pretty straightforward one, but it's good to illustrate the idea. And I'm pretty sure you guys will be convinced that P of X over here implies Q of X. Would you agree? But not the other way around. All right? This one is not the case. All right, so I'm saying that if I know that X is already larger than 0, I can conclude that X should be larger than or equal to 0. That makes sense. On the other hand, if I know that X is larger than or equal to 0, can I conclude that X is positive? Not really, because X could be equal to 0, in which case this one is not going to hold. Right? Easy to justify. So whenever you want to decide whether two predicates has any stronger versus weaker relation, you can try the implication relationship to convince yourself. If you can show that one implies the other, you can decide which one's stronger, which one's weaker, right? Especially when you got a guard condition from the abstract and the guard condition from the concrete. That's really the predicate we want to put together, but that's something we'll see. Okay, that's for the next page. How do you visualize this? Let's use the set comprehension notation that we learned earlier in the math review. Okay, I'm going to put it here. To visualize what's happening over here, you can think about, for each predicate here, think about the set of satisfying values for that particular predicate. For a weaker predicate, it's going to allow more values to be included in the set. For the stronger predicate, it's going to filter out more values from the set, so it's going to be smaller. Okay, let's see what I mean. So you want to think about in terms of the satisfying value. And the way to define that is very straightforward. For example, you can think about the first set. I got all the x such that p of x is actually true. Versus, I got another one, x such that q of x. I think I should really keep lowercase to avoid confusion. P of x and x such that q of x. All right. And apparently here, you can find that it turns out subset relation is the case. And if I can also draw some connection to back your 1090, we knew that there is a way to really connect implication with subset relation. But let's not bother with the detail for now. Okay? How do I visualize this? And if you try the other way around, this way around, it's not going to work, right? Let's now visualize that. Okay, let's say this is green. Okay. I would say I prefer, let's say this is red over here. So this is going to be the set of value that's going to satisfy P, which is going to be larger than 0. That one there is going to be starting from 1, and then 2, and then 3, all the way to plus infinity. Right? So that one is a set of all satisfying value for P of x. And that one there is contained within this set over here. Okay, so you can draw another bigger one over here. This one here would be basically q of x. And I'm pretty sure you know that the value I can put here would be exactly just 0. Meaning that 0 is the additional value that's going to satisfy this, but not this. All right, so when you review the example, you will see. And we say that this particular predicate over here, because its corresponding set of satisfying value is smaller, so it is stronger. Stronger in the sense that it's going to allow fewer values to be included in the set. On the other hand, the weaker predicates is going to filter less value, so it's going to include more values. Okay? Weaker predicates allows more value or values in general to be included in the satisfying value set. On the other hand, the stronger one is going to filter more. Right? You can see include versus filter, right? You can see the word usage here. Stronger predicates filters more values. And you can see it filter out exactly 0, right? All right, so that's about stronger versus weaker. Any question? Of course, I'm using very simple example here just to illustrate the concept, right? Whenever you're talking about a more complicated predicate, basically what you got to do is you're going to make sure if you can establish some implication relation between the two. If you can, that means you're able to say one is stronger, the other one is weaker. If you cannot establish such relation for implication, you cannot say that. Okay, that's my point. But typically, in the context of our proof obligation for refinements, especially guard strengthening, usually you will be able to establish, typically. Okay. All right, that's background information number one about weaker versus stronger. Good. And then, next stage, I want to talk about why do we need guard strengthening? All right. And then once we got these two pages done, it will be much easier to look at the guard strengthening proof obligation. All right. Let's set up the context. So we talk about refinements. And why guard strengthening? Specifically, the rule tells you that the H should imply the G. And the H over here is a concrete guard. And the G over here is the abstract guard. All right, I want to show you something very quickly. Right, just go back to the model so you can see what I'm really talking about. So if you go back to, for example, the model over here, you're going to somehow prove about guard strengthening for every pair of the abstract and concrete events. For example, this will be the first pair to prove about it. And this will be the second pair about MLN. When you talk about this first pair over here, you want to show that the concrete guard over here somehow implies the abstract guard. Somehow. Number one. Number two, when you look at this pair over here, you want to somehow show that the concrete guard implies the abstract guard over here. All right, that's something I'm sketching, right? At least you know what I'm referring to. But let me go back to this page over here to understand why H implies G. That's important, all right? So there are several things I would like to say. Number one, what's the principle? The principle over here would be, whenever we talk about a refinement, its behavior should be consistent with the abstract behavior. Okay? A refinement's behavior should be consistent with the abstract model's behavior. So what do I really mean consistent? I'll elaborate that a little bit later. Consistent with. Okay? So when I talk about refinements here, it could be, for example, M1. That's one example. And when we talk about abstract model, it will be M0. Another more technical term to say would be, there's no new behavior that's going to be introduced. No new behavior introduced by the concrete events. Right? So this might be more relevant to the rule. No new behavior should be introduced by the concrete events. Okay, that's a principle. before we talk about H implies G, should be the case. Let's talk about the other way around, which might be commonly confused. Why G implies H doesn't really work. That's important to see. All right. Let me start from number one. If I do G implies H, all right, so the G here is the abstract guard. And the H over here is a concrete guard. We want to learn why this one is not the case. Why not? All right. What we learned earlier in the page over here is going to help us. All right, let's now try to visualize it right away. If somehow we want to show that G is stronger than H, visually speaking, what's going to happen? Visually speaking, we're going to have the diagram like this. One here, and one here. And which one should be the smallest circle conceptually? G. G, right? Because here, you see, G is stronger, so that should be the smaller one. Okay, be careful, okay? That's okay. It's okay to be wrong during the lecture. No worries. So here, we got the G here, and we got the H over here. All right? Now, this guy here is the abstract guard. And this guy here that's weaker will be the concrete guard. Having this relation holds is going to be problematic because it's going to violate the principle over here. The principle says there should be no new behavior introduced by the refinements. But by allowing this, we're going to allow some new behavior to be introduced. That's a violation. Why? All you got to do is think about, if I can find a point over here, what does that really represent? Because I know that G somehow is stronger than H, like what we said earlier. Like this predicate over here is stronger than this one here. I can find some witness to show that, right? Now, what will be this particular witness? It's not a specific value, but what will be the condition? All right. I'm going to tell you right away. You're going to think about it. That one there is going to be outside of G, not G and H. Agree? And what does that mean? That one really means the following. Not G means the abstract version of the events, because it's negation here. So that means that particular abstract event is disabled. On the other hand, the H over here tells you that the corresponding concrete version of the events is enabled. First of all, we want to understand that, right? And why is that problematic? And what we said earlier in this example here is going to help. Sorry, let me just divert a little bit. If you remember this diagram over here, right? I'm going to redraw. At this particular state over here, we see that given that this is enabled, at the same time, this is also enabled. So we do have some correspondence. However, if you say that you're able to, at this stage, make a transition over here from here to here, but in the corresponding abstract world, you cannot make that. That means this particular transition here is inconsistent with the abstract world. You're creating some new transition that has no correspondence in the abstract world. This will be some new behavior you have introduced. All right. So I'm going to write it down. Right? It's a very important kind of intuition to get, right? It will take some time. So the way to visualize this would be, think about, we got some abstract states. We got some abstract states over here. So abstract states, we have some concrete states. And somehow we got here not G. And here we got H. Oh, beg your pardon, the other way. Sorry about that. Because H over here is a concrete guard. So we got H over here. That means we do have the corresponding concrete transition. That one can occur. On the other hand, we got not G. This one tells you that the abstract events is disabled. So here we got some inconsistency. For the same consistent pair of states over here, somehow the concrete transition can occur, which is new behavior, but the corresponding abstract transition is disabled. So we don't have any consistency here. All right, so that's number one, to explain why G implies H is not the way to go. Number one. All right, let's at least finish this, and then I can do a little bit of we'll see. Okay, at least I want to finish this one. That's important. Okay, number one, we already justify why this one here is not the case. And how do we interpret this? That will be number two, right? This will be the correct one. The interpretation is not that surprising. We're simply going to say, if a concrete transition is enabled, the abstract transition, that's the corresponding abstract transition, is always enabled as well. The corresponding abstract transition is always enabled as well. That tells us we don't really have this kind of situation. If this is already enabled, it's guaranteed that one is also enabled, right? So that's a different. That's why when we flip the order of these two operands, it's going to mean different things. Okay. So this one tells you no new behavior by the refinements. All right. That's the second one. And one more. Okay. Do you guys remember contrapositive for implication, right? There's another way to really interpret this. We know that this guy here is the correct one. You may also want to think about what it means when we apply contrapositive. So number three, that will be the final one. Not G implies not H. Again, the G here, not G here, means the abstract events is disabled. And here, not H means the corresponding concrete events is also disabled. Notice that I say disabled because I got a negation over here. All right, so that's the final interpretation. So the way to think about this is like this. Whenever I got the abstract transition not being possible, to really make sure it's consistent, I just got to make sure the concrete one is also not possible. So that way, I don't create any new behavior. The new behavior is only created when I have some transition possible for the concrete, but I don't have the corresponding one possible for the abstract. I want to disallow that. How does this one disallow that? That one is to say, if I got this one disabled, that one got to be disabled as well. All right, that's how we see the contrapositive. All right, so you got 3 predicates over here for you to think about before Thursday. You got number 1 here, that's invalid. You got number 2 and number 3, they're both valid. Okay, think about it. Okay, so these are the 2 background pages I would like to talk about. That will just make it much smoother when we talk about guard strengthening. Any questions? All right, we got 5 more minutes. I think what we can do is we can try to look at the proof obligation and try to formulate it, and we are done. Okay, so that's the actual proof obligation. You can see we got H here implies G. H here implies G, right? So what does it say? That tells you this will be the proof obligation for guard strengthening. And notice that the G over here is indexed, right? I here, which can be either the guard for ML out, or it could be the guard for ML in, either one, right? So now the first question to ask, based on this proof obligation rule, how many sequence should we really generate? It depends on how many concrete guards we have. We got concrete guard number 1, we got concrete guard number 2. So we got 2 sequences to generate. Okay? So question number 1. It depends on the number of concrete guards or concrete events, right? So you can think about the I over here. It could be either for ML out or for ML in. All right, so let's now try to sketch the proof obligation right away, and then we'll try to prove it on Thursday. Okay, so we got about 4 minutes. Okay, what about a naming convention? So we're going to put, you can think about this is the first pair, and then we got a second pair over here. So we got ML out. Okay, let me just make sure I got the name right. Yep. And then GRD. Pretty simple here, right? We're basically saying for the refinements, we got to make sure the concrete guard for ML out implies the abstract guard over here. So that's the first proof obligation. And the second one here will be ML in, and then guard strengthening. So these are the 2 proof obligations we will need. All right. Let me do one of them, and the other one will be your exercise. All right, let's start with here. So this will be all the axioms. And the axioms were actually from the abstract model. I don't really include it here, but you can also look it up. It will be D is a member of natural number, and also D larger than 0. And for your reference, this one here is axiom 0,1. This one here is axiom 0,2. You can look it up earlier in the page. I just don't have the space on the page. And this guy over here will be the abstract invariance, which will be over here. So I'm going to put n is a member of natural number, and also n less than or equal to d. Okay? So this is invariance 0,1, invariance 0,2, right? Of course, when you actually put the answer in the exam, for example, you don't necessarily have to put this. That one just like a comment for you, right? All right, we're done with this, we're done with this. And this will be the concrete invariance, every one of them, all right? The concrete invariance will be over here, every one of them. A natural number, B natural number, C natural number, and also, I just don't have space, I'm going to write it here. A plus B plus C equals N, and also A equals 0, or C equals 0. All right, here comes the most critical bit. This guy here, H, is the concrete guard. Right? Just remember, we're going to need this. Right? Concrete guard implies abstract guard. Let's say we talk about ML out. Concrete guard will be here. So I'm going to put A plus B less than D, and also C equals 0. All right? So the most important part for you to pay attention to will be over here. And I'm now done with this particular part here. What I got to do will be, I got to put a turnstile. And what I need will be this part over here. This will be the abstract guard. Okay, the abstract guard. And since we are now talking about ML out, so that's the only one I need to put. N less than D. So that's the solution for this particular proof obligation. Your exercise you really want to try will be for this one here. What should that be? You can see it's going to 1 minute, and then we're done. Sorry, give me 1 minute. I do apologize. Give me 1 minute. So when you do the exercise, you can see this part over here is going to share. This part here is going to be all the same, right? This part here. The only part that's going to be different will be the concrete guard for MLN is going to imply the concrete abstract guard for MLN. All right, thank you so much. Do the exercise, and then we'll continue from Thursday.